So this is a laboratory for domestic wastewater. You can see all the equipment, the balances, and the exicators, the oven, and every equipment for the determination of the total suspended solids, which are needed. Okay. And here we have some equipment for settable solids, which is a parameter of domestic wastewater and total suspended solids. Here we have an example for automatic and manual filtration unit. You should know at least the right units, the barrettes. I have used this because before I studied in Höxter, I used to work for a chemical industry as well for 7 years at Bayer Leverkusen in the organics plant protection sector. So during my education, we only used the barrettes on the right-hand side. We haven't had the opportunity to use these automatic barrettes the students can use today. Okay. Here you can see the analytical balances and turbidimeter we are using for the lab training as well. And these are stationary and mobile jar test equipments. You might know this. This is very famous on the right-hand side. It's from Scandinavia, so you can put it in a suitcase and do some experiments at customers' space or wherever. Here we have some photometers, a big one on the left-hand side, which can do a scan with, I think, 1 nanometer spacing. So you can do delicate equipment with delicate analysis with these. In the middle, you see a normal photometer which has been used for round cuvettes. For this fast determination of, for example, COD or phosphate or nitrate or something like that. This is mobile equipment, pH measurement, conductivity, and dissolved oxygen. So we have several of these units available in the laboratories, even with suitcases for mobile measurement. And at least to get exact volume, we have that certain kinds of pipettes and technologies. So these are some pilot plants, or a little bit smaller than pilot plants, for the lab training using Professor Fettig. So we have the deep bed filtration here, rapid decarbonization over here, and ion exchange, this small column over here. All the units are used in the practical training program. This is for the debridement of or the oxidation of organic substances in water, in ozone generator. And this is a nanofiltration unit with a high pressure pump in the back. This is an eccentric screw pump which can deliver high pressures. Here is a part of a lab scale municipal wastewater plant. So it's modular, so we can integrate phosphate removal, we can integrate denitrification prior to the oxidation process or the post-process. So we have several units like these, and they can simulate different type of municipal wastewater treatment plants. This is a nice unit. It's a flotation plant from company Enviplan, which is very famous because of the very, very small bubbles they can produce here. They have a special equipment, a special kind of nozzle to produce very, very small air bubbles, a factor of 3 to 5 smaller than comparable units, and the efficiency is really, really high of these units. So this is an analysator for the determination. Ah, that's nice. Thank you. This is man. This is a TIC and TNB, total nitrogen bound, and this is pretty new. And here in the back you can see an IC for, you know, what is it in English? Ionic chromatographic? Is it? I think so. Yes. Okay. So this is a supply with deionized water. We have a big plant down in the cellar which delivers this unit here, but here we have some ion exchanges and one activated carbon column to get more purified water from it. It's been used for analysis. Okay. So now let's come to the lab training. The boundary conditions, depending on the study program, if you're studying bachelor or master, different practical trainings have to be attended. So it's a must. The students have to take part in this kind of education. And the students have to evaluate the data obtained from the experiments they're doing, and they have to write reports. And the reports are reviewed. So if the reports are okay, the student passed. If they're not okay, they have to write a new report until the results are decent. The theoretical background is given within lessons before the training. So they are being introduced about what they are going to do in the laboratory. And during the lab training, they are asked, what are you doing here? What it's good for? What's the purpose of this? And some of the students who don't know the answer, believe me, know the answer the next time. Because it's not very nice being asked, what are you doing here? And you haven't got any idea about what you're doing. So the objective is a combination of training of manual skills, the usage of the equipment itself. How do I measure the pH? How do I measure the total suspended solids and other parameters? And of course, scientific skills. So let me give a little bit of overview what we are doing in the laboratory. So this is a lab training of the domestic wastewater for the bachelor. This has been carried out by Martin Oldenburg, so some of you might know him. And the first part is an analysis. How are certain parameters being determined? Measurement of turbidity, color, odor, settleable solids. You know that parameters, if you get a sample, you have to determine the color. Is it turbid? How does it smell? And such easy parameters. We're starting with an easy one and getting more complex up to biological oxygen demand, total organic carbon, dissolved organic carbon, of course, and parameters like chemical oxygen demand, which is a sum parameter, which is very important, for example, for industrial wastewater, and dried matter, glowing residue, and so on. So the objective here is training of skills for the proper measurements. How do I measure properly? So everybody can measure, but the results may vary in a broad spectrum. So this is the equipment being used. These are only examples: the pH measurement, the turbidimeter, these units for the filtration and the settleable solids. Yeah. So these units are being used for the determination of, for example, COD, nitrate, nitrite, ammonia, and other parameters. So this is a heating unit here for cooking the COD. I don't know how you're doing it here, but we are using very aggressive oxidation substance. Yeah, this we've seen before, the DOC. That's good. And this is a bottle method for the determination of BOD. The sample has been filled in here, and we have a measurement device screwed on the neck of the bottle, which measures the pressure. So the oxygen's been taken from the air in the bottle, so the sampling volume is only, let's say, up to here. So you have an area of air over the water, and the oxygen has been consumed for the oxidation process, and you can measure because the oxygen is missing then, and you got a negative pressure in here, so you can read the direct oxygen demand for the sample. This is a sample for analysis sheet with certain parameters. It's a little bit small, but it's a lot of minutes, date, time, color, odor, turbidity, and so on, up to the nitrogen parameters, phosphorus, total phosphorus, COD, TOC, and so on. So this is the sheet you use for characterizing, for example, of domestic wastewater. This is a unit, very simple, to determine the biological respiration. So it's possible to record the activity of bacteria being degrading some organic substances. So if you take the next slide, we can see the result. Yeah. So you can see here, this is the time axis, and this is the concentration measured of dissolved oxygen in the sample over the time. And you see this decrease. And here we've got several different types. Sometimes you have some substances inside the water preventing or stopping the biological processes of degradation. This inhibition, like this types here, this inhibition can be measured by such a test. So you can say over the time whether there is a respiration of oxygen in the sample, which means that the water is biological degradable, or you might have some preventing substances in the water which blocks the process of biological degradation. That's the purpose of this. So this, some of the engineers might know, is a small test for the mean residence time distribution. So you know the different type of reactors been used in chemical industry as well. So you can have a full steered reactor or a cascade reactor or a pipe reactor, and the behavior of every reactor is different. So the hydraulic mean retention time within such a system is completely different. And with such a small unit here, so you can put in some walls here, so you can make it from a pipe reactor to a fully mixed reactor and measure the hydraulic retention time by adding a sample here. We use deionized water in the system and the salt solution injected by the syringe at once, and then you're measuring the conductivity in the effluent over the time. Every minute you do a measurement, and can you show the next one? And here you see this is a real measurement of students for a stirred reactor. You see the conductivity, you see the time, and this is the behavior of the system over the time. So they're doing it for different types of reactors, and they have to compare it. Okay. So this is the lab training now of water technology. and we do a precipitation by adding aluminium. And the objective here is a determination of the turbidity. In every beaker glass, different concentration of aluminium has been added, and after a certain reaction time, the stirrer has been switched off, and in the supernatant, the concentration, the turbidity and the concentration of phosphate and SAC254, this is the spectral absorption coefficient at 254 nanometer, is being determined. Related to the aluminium concentration and the pH. So this has been done by several groups of students. One group does it by pH at pH 6, the other pH 7, pH 8 or 9. Can you show the next one so we can see it here? So it's pH 6, 6.5, and 7. So this is the curve for soluted phosphate as a function of the concentration of aluminium. So you can see the higher the concentration of aluminium, the lower the concentration of phosphate P. And this is the spectral absorption coefficient at 254 nanometer as a function of aluminium at different pHs again. And you can see that with a higher concentration of aluminium, we can achieve a lower absorption coefficient. So this is just a demonstration for the students. It's a continuous operating system for the flocculation. So we have 3 chambers here, steered at different speeds, from very fast to very low, like it's been done in practice. And then the sedimentation basin over here. So this was not under operation, therefore you can see no effect. But I took a picture of this just to give you an impression what we are doing in Höxter. And here the concentration of TSS has been demonstrated, steering rates and so on, and hydraulic retention time for the flocculation and the sedimentation state. So one have to make sure that the particles at least have to sedimentate at this point. Okay. So this is separation of solids by direct filtration. The purpose of this is to measure the turbidity in the effluent of the filter system. So it's been operated upside down. At different horizons, we have this connected these pipes where you can record the pressure lost over the height, and this has to be recorded over the time. It's very simple. So we have hydroanthracite and sand here. So the system can be cleaned after we're doing the experiment. We can rinse it with water from the bottom to the top, and the material will not be mixed because of the different densities. So turbidity in the effluent, the pressure lost over the time, and the filter loading have to be determined. To the next, please. And here you see the Michaud diagram. I know you're familiar with, I think you're familiar with that. That the pressure lost at certain heights. Here you see the filter system itself. It's sand, hydroanthracite, and here we have the water above the filter system to give you a little bit of pressure difference, which is a force for the filtrating process. This is a sketch of the system here. And here we have the pressure loss as a function of the operating time. So increasing operating time, increasing pressure loss, it's overall. It's a pressure loss at this point here. And this is the pressure loss for the different horizons. This is a sketch of a cross-flow ultrafiltration system. So we have a small model system in the lab which has been charged get some filtrate out here, and we get an increase of the concentration in the circulating system. So we can show it on the next. So here we got the transmembrane pressure, and we have the flow in milliliter per minute related to transmembrane pressure. Here the pressure lost in bar, and again the filtrate milliliter per minute related to the pressure loss, and this is the increase of the turbidity in the circulating water over the time. This is for the determination of the adsorption equilibrium of activated carbon. So there are different tasks. The first task is to determine the isotherm of substance by bottle point method used by this shaker. You might know this one. You have your samples at different amounts of powdered activated carbon to it and shake them for 24 hours or 48 hours. Then you stop the process and you take filtered samples for the analysis maybe of POC or other parameters. And this is the bottle point method. And the second is the determination of the internal mass transfer. This is a single substance we are using for it, an organic substance with granular activated carbon. It's been done by this stirred device. So this is not only a stirrer, you can screw it and put some granular activated carbon inside. So you have two sieves and screw it together. You know the mass of activated carbon, and then you start the stirring process. And over the time you're measuring, let's say every hour or every 2 hours, you take a sample out of the beaker glass, and then you do analysis, for example, SAC 254 or POC or whatever, and you can see the decrease of the concentration over time. So we see here the diagrams. I'm not an expert on this. Let me say a hobby of Professor Fettig. So he did his PhD in absorption processes on activated carbon. But here we have for the stirring device the contact time, which means the stirring time in the system, and C to CO, which means the concentration measured at a certain time related to the concentration at the beginning of the process. So this might give you this might give you an overview about the result of this kind of experiment. Okay. So this is about ion exchange process. So you can operate a column of an ion exchanger as a column, or you can do a titration of resin, which is shown here. So we have a resin sample in here, and the students do a titration of this ion exchange resin in H+ form with NaOH, with caustic soda, to determine the capacity and the exchange of chlorine by nitrate, the bottle point method, and they're doing some experiments with the loading of a column, which is shown on the next slide. But the objective here of this experiment is a determination of the total capacity of the ion exchanger, and of course a separating factor of a strong base anion resin for the exchange of chlorine nitrate, and to determine the breakthrough curve of calcium. So for the softening of water, ion exchangers are often used, as you might know, in dish dashers, for example. So the determination of the breakthrough curve is one of the tasks. So here we have a lot of evaluations show you this one here. So we have the concentration of H+. This is the operating time in minutes, and this is the concentration of Ca2, calcium, in the effluent. And you can see that at this point, the resin has to be, what is it called, regenerated, because the capacity is over. Okay. This is a column filled with, what is it? Is the name of it? It's a filled column. Glass, plastic, whatever. You know it? No. I don't know the English term for it. So it's a filled column, which has been used for the gas exchange process. So we feed water up the top, and that's the water that has been treated, and the air from the bottom, and then we have the process of gas exchange, of course, and we're stripping out carbon dioxide, which changes the equilibrium of calcium, and the water can be treated prior to a distribution in pipe systems or whatever, as tap water, by this process. So the task is the recording of the concentration of dissolved oxygen in a distilled water sample, which is not shown here. This is task 2, stripping of carbon dioxide by counter current flow at different operating points. So we vary the relation between the volume, the flow of water and the flow of air in that column, and determine for this different ratios the results. So this is the result from one experiment which is not shown on the slide prior there, but you can see here what is it in English? The different HTU, NTU for the dimensioning of columns. Some chemical engineers should know it here, which are related to the design of such systems. You got the NTU, HTU, and the NTU factor for the height and the diameter dimensioning of columns for the exchange. This is a lab training, hardening and softening of water. So if the water is too hard, containing too much calcium, it has to be treated to get a balance of the equilibrium. And if the water is too soft, it's not good as well, because it's calcium aggressive then. So you have to put the water into a balance before you distribute it. And this is the task for these experiments here. We have a marble filtration here, and we have a rapid decarbonization system here, which is filled with small pellets of calcium carbonate. And the water is being raised in the pH. So you raise the pH of the raw water. You want to treat by 1 or 2 units, let's say to 9 or 10. And then the water is being pumped over this system, and the bed is being fluidized. So it's a fluidized bed. And the surplus of calcium is being precipitating on these small granules. So you soften the water by this kind of treatment. And opposite, here you do a filtration with marble. So this column is filled with marble as well. So at least this is marble as well, but different size. And here we got different horizons for the sampling. And the students take samples at different horizons, which corresponds, of course, if you got a continuous flow with the contact time. And they have to do a determination afterwards with the samples been taken there for calcium concentration in the water. So this is the result of the marble filtration. So you can see this is a depth of filter, which are the sampling points you could see on the last slide. And this is the calcium concentration. At certain points, you can see these are real measurements. Sometimes it happens that the values are not ideal, but that's life. And this is the determination of carbon dioxide. And here we have the results for the pH and the saturation index of the equilibrium corresponding to the depth of the filter. These only a few words. Oxidation of toxic substances or complex organic substances by ultraviolet light and H2O2 is an old method, like Fenton, probably with iron 2 salts. Here we use only UV and H2O2 in different kind of reactors. So this is a continuous flow reactor. This is a simple split reactor. We compare the results then afterwards. So we're doing it by the sum parameters SAC 254 and SAC 436 with a photometer. And another task, which is not shown here, is oxidation with ozone, which is more aggressive, which is more dangerous, of course. But the results are being compared after that lab training for the oxidation of organic substances. So here you can see the time axis again and the concentration of H2O2 in the solution. So you can do a good determination of your substance directly, or you can say, okay, what's the start concentration of H2O2, and if H2O2 is being used for an oxidation process, the concentration decreases, and thus can be recorded over the time as well. And here we got the SAC 254 and 436 over the reaction time. I have to find out, I guess this is the 254. So over the reaction time, we can record a decrease of the sum parameter for organic substances over the time. Okay, that should be enough for this. Many input. So thanks a lot for your attention. Do you have any questions?
If you have few time for your questions.
Sure, I have one question. It's very interesting to use measure POD fighting, but by what means you prevent influence of carbon dioxide reducing parametric method of measuring POD?
You mean the influence of CO2?
Of carbon dioxide.
Yes, the carbon dioxide is being absorbed. You use the caps have inside
What substance is used?
NaOH.
Oh, thank you.
NaOH pellets which absorb the carbon dioxide. Yeah. That's a good question, because otherwise you would increase.
Yeah.
And you would not get the proper result.
I have another one.
Yeah.
Please tell us, you know that after treating by ozone, you can release a lot of radicals.
Yes.
Are they toxic substances, and how long they exist in the liquid?
That's a good question again. I'm not an expert on this, but I would say it depends on your raw material. which is being oxidized.
Mhm.
So let's say we have EDTA.
Mhm.
You're an expert on this.
And probably the last question. When anyone tried to remove water from sludge,
Yes.
he used different methods, and after that, anybody tried to return this effluent into the beginning point of water treatment technology. For example, we obtain effluent from anaerobic treatment of sludge,
Yes.
and after that we have some efforts to discharge this effluent in, for example, aerotanks.
Yes.
How many toxic substances exist in this effluent?
It depends always on the matrix in the water. You have to determine it for every individual application. If I do an anaerobic digestion and I do a post-treatment aerobic, so I have to determine for the special kind of water, for the special kind of substances in the water, whether they are toxic or not toxic. It's the same with the ozonization of the water. So you can have harmless substances or you can have toxic radicals, and you have to do post-treatment. For example, after the oxidation process and the biological process, you have to have an absorber stage also with activated carbon. So, but it depends on the water matrix.
Well, and probably the last question. How there exist a simple test for evaluation toxicity of effluent?
There's a respiration test, for example. The respiration test can be applied for this. So you can see if the substances are toxic to bacteria. And other tests as well, the fish test, you can use Daphnia, other biological tests, but I'm not an expert on biological. I'm working on industrial waste-based treatment.
Thank you.
You're welcome. Yeah.
How many students do you have in one group?
One group is maximum 12 students because the capacity in the lab is limited, and we have approximately 3 or 4 groups of students depending on the semester, of course.
So how do you manage the experiments? You have like 12 students and they have, for example, Eugene. So it takes 5 days. How about the other students? How do you
Yeah,
manage?
this has been some work has been prepared in advance because of the time. It's limited. For some experiments, they are divided into groups, and one group, for example, the precipitations. Also, you work on pH 6, you work on pH 5, you work on pH 7, which means 3 groups doing the same at different pH, and this has been done with the respiration tests, for example, as well. So one group does a test with non-toxic water, and the other groups get some toxic substances, and they have to be determined then the respiration. And after all the groups finish, the results are combined and compared. Any other questions?
Thank you very much. Okay.
Thank you.
Встретимся после перерыва. Теперь у нас продолжение лекции, к нам присоединятся студенты. Ланч.